So whole numbers. We have to match these terms with definition and example. We know that whole numbers would be things like 0, 1, 2, 3. And the definition that best fits this is also known as counting numbers. These are positive integers and 0. So those would be our whole numbers. Next, we have rational numbers. Rational numbers are numbers that can be written as a fraction. Okay, so any number that you can write as a fraction is rational. And so looking at the options we have for examples, there's pi. And that isn't a fraction, right? It's a decimal that goes on forever and it never ends. And if we look at the next one down, we have -1, -2/3, 0, 1/4, and 1. So we have some fractions there. So that could be an option. The next one down, we have -2, -1, 0, 1, and 2. None of those look like fractions right away, right? But we could write each of those as a fraction. So maybe. And very bottom, we have -1, -1/2, 0, 3 repeating forever, 1, and the square root of 2. Now the square root of 2, we can't write as a fraction. So this one's out. Rational numbers are going to be this setup here. Okay. Integers are positive or negative. Whole numbers and 0.
No, Yahweh.
Irrational numbers are things like pi. We can't write these as fractions of integers. And that leaves real numbers. These are all rational and irrational numbers. And it would be that very last example. How's it going, Jennifer? Can you hear me okay?
Yeah, I can.
Can
you hear me?
Okay.
Oh. Yeah.
So I was a little worried that you wouldn't be able to understand us if we had our masks on.
Yeah, I can actually hear you guys I can hear you really well anyways.
All right, good. So what we're doing is we're going over the entrance questions. And there were 3 parts. We had matching vocabulary, writing the symbol, equal to. That's just our equal sign. Next one is less than. This one, the small. Towards the little number. So x would be less than some other number. Greater than or equal to. We're going to flip the sign and put a line underneath. Less than or equal to. It's kind of like the less than above with that one line. And last but not least, greater than. Any questions that you have so far?
He just made it with that big truck.
then this last part, we get to do a little bit of rounding. We're going to round to the nearest tenth. So we're going to round to the 8, but we always have to look behind. 9 is greater than 5, so this becomes 9.
Three people
We
died.
need to figure out if 9/11 is greater than, less than, or equal to 18/20. So what the easiest way to do this when we're comparing fractions is to find their decimal points and then compare the decimals. We take 9 divided by 11. We get
No.
0.81, and that repeats forever and ever and ever. 18 divided by 20 is 0.9. This is less than. Next up, we want to place these numbers in order from smallest to largest. Same strategy, I'm going to turn these fractions into decimals. It's going to be easier to compare, so 13 divided by 8 is 1.625, 0.75, and is 1.6. Our smallest number is 3/4. After 3/4, it's 1.2. Oops. Then it'd be 24/15. And 13. Final question wants us to circle any prime numbers.
Okay, Jimmy.
Prime numbers are ones that we can't divide by anything except for 1. 96 we can divide by 3. 85 we can divide by 5. 53 we can divide by 3.
It's okay.
79,
It's called.
not anything I can think of off the top of my head. And 77 I can divide by 7. So the prime number here is 79.
What's this credit?
Are there any questions over these?
Where's my car? This is
So I'm going to hand out a paper that looks like this.
no, stop my big credit.
And if it wasn't for COVID,
Jesus.
of you would be measuring.
Oh, there you go.
But
Use it.
because of COVID, I'll be doing the measuring for you. So we're going to get the height of the table, width of a door, length of a calculator. We're going to look at a cylinder and a pencil. Maybe a textbook. We'll see. So would you like me to use centimeters, inches, feet, or meters? Inches? Okay. So the height of the table is 29.5 inches. the width of a door. $35 and 5/8. Length of a calculator is $5 and 11. $30 seconds. Seems like an awkward size for the diameter of a circle. We have 2 and 5/16. And the length of a pencil, I'm just going to grab one from up here. $7 and 7/16. Since I have a textbook, we'll just do the diagonal measurement. $13 and 11/16. Now, the next thing we're going to look at is the accuracy and precision of our measurements. But accuracy and precision have different meanings than probably what most of you are thinking of right now. In math, accuracy typically refers to not how accurate your measurement is, but how many significant digits there are and precision is the last place value of the last significant figure. I'm going to use digit and figure interchangeably. They just mean the same thing. But that means we also need to define what significant figures and digits are. Sorry, that looks like chicken scratch, doesn't it? It says the last place value of the last significant figure. I just know that if I press the mouse button, I'm gonna lose everything. I don't wanna do that necessarily. All right, but there are some rules for significant figures. Oh my goodness. So the numbers 1 through 9 are always significant. We will always include those. So far, looking at our measurements, it seems as though they all have pretty high accuracy, meaning they have multiple significant figures. I don't see any zeros, and right now it's a good thing. But what we're going to see as we move on throughout the night is that zeros aren't always significant. When they are between significant figures, or when they're to the right of a decimal point. So this means numbers like 101. Zeros between two significant figures. 1, 2. We have 3 significant figures. If this was 3.0, 0 is to the right of a decimal point. It counts as a significant figure. We now have 2 significant figures. So this is what those mean. Probably shouldn't be writing on the board with an open marker in my hand. That could be bad. So let's talk about when zeros are not significant. we're not going to count zeros when they're at the end of a whole number. We're also not going to count them when they're to the left of a decimal number. If this was 58,000, since that's a whole number, those last 3 zeros do not count. We ignore those, and we have 2 significant figures. It's still 58,000. I'm not saying that we get rid of those zeros completely. It's when we go to look at accuracy and precision, those zeros don't account for very much. And if we had 0.014, the 2 zeros in front, since they're to the left of our decimal number, we ignore those. 1 and 4 count. This also has 2 significant figures. So the best way to determine accuracy is to not use fractions, but instead to look at decimals. So we're going to put all of these measurements into decimals. This is 29.5. There are no zeros here. So how many numbers do we have in our measurement? Casey says 3. So the accuracy is 3. Significant figures. If you just wanted to write 3 here, I'm okay with that. The next one, 35 and 5/8 becomes 35.625. How accurate were we this time around? Yep, so we have 5 significant figures, no zeros. It's easy when there's no zeros. (11/32) is a fun fraction. It's a fun decimal. 34375. This time we have 6 significant figures that were accurate too. The cylinder, we were accurate to 5 significant figures. Length of a pencil, 0.4375. It's also 5 significant figures. Anyone want to take a guess at how many significant figures the textbook would have?
Ooh,
6.
we did
6?
6.
Yep.
Jennifer says 6.
When the college book.
Anyone agree with Jennifer? Ava says yes. I will agree with that. We have 13.6875, and that would be 6 significant figures. So let's flip this over. And look at some cases that have 0.
That's entire Twitter.
Oh man, I'm putting the cart before the horse. You know, we didn't talk about how precise those numbers are. We'll come back to it. We'll come back to it. Determine the accuracy of the number. So we have a 0 right here. It's between a 1 and a 5. Because it's between non-zero numbers, we count it. So 1, 1, 0, 5, 7 gives me 5 significant figures.
Okay, let's do that.
We want to, for number 2, determine the precision of the number. Remember, this is the place value of the last digit.
Oh my god.
So that means the rightmost. That's this one right here behind the 7. The hardest part for students is remembering the place value.
I didn't do it.
And we have to find the decimal point. So the decimal point is between the 6 and the 1. The first place after the decimal point is always the 10th place. So it's tenths, hundredths, thousandths. This last one here is 10,000. I want to emphasize that you put the THS there on the end, because if you don't, it means 10,000, and that is on the opposite side of the decimal point.
Was that the answer?
Yep, so the 10,000th place. Or you could just write 10,000.
don't do that. The engine smoking went public.
Number 3 asks us, are the zeros significant in the value
What's this one?
472,800. This one has 2 zeros at the end of a whole number. According to our rules, no, these are not significant. If I'm going too fast, you can definitely stop me and ask questions at any point. So, we'll see. Sometimes it's fun. So we want to determine the precision of this number. We have 2 zeros here. The first 0 we know is significant. It is between a 4 and an 8. It has to be significant. What about that last 0? Is that going to be significant? I think, was that Ava or Jamie that said no? Jamie said no. So are we looking at a whole number?
Oh my god, it can still.
No, because there's a decimal point here.
I can still drive this, do it.
And
Oh no 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 no.
this is where
no, 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 no,
significant figures start to be a challenge. This last 0 is at the right of a decimal number or a decimal point. So this time around it gets counted. So sometimes, like if the whole number, it doesn't count. But if it's a decimal, it does. Tenths, hundredths, this is the thousand. Last but not least is number 6. We want to determine the accuracy of 700. It should just be 1. The whole number, so those zeros do not count. Okay, I need to go back and look at the precision for each of these. Because we didn't talk about this. The first one was 29.5, correct? What's the place value that the 5 is in? The tenths. So this was tenths. And the width of the door was 3.625. So thousandths.
40, 40.
The length of the calculator, that's the one we had to go to the 30 seconds, correct? So this one's going to have a precision of, let's see, tenths, hundredths, thousands, 1,000. Is there 4 behind the decimal? No, there's 5 behind the decimal point, correct?
Bad idea.
100,000.
Come on, let me help. Okay, there we go. Oh my god, this is good. What are you doing? Why? I'm looking for.
And then the last 3 should all be a precision of the 10,000. They should all be 16ths.
Yeah, restart.
Okay, the
Restart.
next thing I have you do
Sometimes it happens.
is work with significant figures and rounding.
Like that.
And I'm anticipating there to be questions about whether zeros are significant or not. Definitely use the calculators that are available to you. And I'll give you, I don't know, 10, I'll see where you're at in 10 minutes. First off, we're looking at 82 divided by 28, and you get a pretty big decimal point, but it says they're out to the 100th place. This is going to be 2.93 after we round. The next one says to round to one significant figure. So this would round to 70. Sorry, negative 70. Next up, round to the nearest 10,000. That gives us 20,000. (36) divided by negative 6.18. We are going to round to four significant figures. This is negative 5.825. Round to the nearest tenth is 13.7. Round to the nearest whole number, that would be 1. The next one says to round to one significant figure. This one you have to think about your zero rules a little bit. If a zero is in front of a decimal number, it usually doesn't count. So 0.04, those two zeros don't count. So it's 0.04. (1.081) plus 2.604. We're going to round that answer to three significant figures. 3.69. (50) divided by 32. We're going to round that to the nearest thousandth. 1.563. Finally, we're going to take 101, times it by 5, and subtract 27, and round it to two significant figures. 480. So 0 at the end of a whole number doesn't count as a significant figure. So what we're going to do is we're going to take a break, about 10 minutes. Yeah, so the homework's going to be to finish the second section. So it's significant figures, operations with significant figures, properties of operation, right? But while you're doing that, there's some very specific instructions in that section, right? You'll watch a video on operations or you'll watch a video on significant figures, which is similar to what we did today, but it might just present it in a different way, especially if there was a lot of confusion and if you got to ask any questions, it's a good review. But if you feel like you've got a good understanding of significant figures, you can just click next and start on the quizzes. But eventually it's going to say that you need to take and make flashcards. And I thought I would at least get you started with some flashcards. If I probably not enough flashcards. And some of you are probably getting more than others, which I apologize for. I'm just kind of grabbing a stack and handing them off. Because there's a lot of properties of operations that you're going to have to know. You're going to have to know all the properties of addition, the property of subtraction, the properties of multiplication, properties of division, properties of exponents, properties of radicals or roots, and the properties of algebra, also known as the equality property. I think there are like 35 to 40 properties. Actually, no, that sounds too high. 25 to 30 properties, roughly. But I want to show you a video on how to make effective flashcards.
Google Fi, a phone plan by Google. Stay
Can
connected.
you hear that okay back there, Ava?
Hotspots
Or do I need to
hovering.
turn it up?
So no Wi-Fi, no problem.
This is a flashcard. More specifically, it's a bad flashcard. And by the end of this video, you're going to understand exactly why, because today we are talking about how to make effective flashcards and how to study them more efficiently. Now, flashcards are an incredibly powerful learning tool because they promote active recall, the process of actively retrieving memories out of your brain, which is one of the most efficient learning strategies there are. But flashcards are tools made by human beings, and as you probably know, things made by humans come in varying degrees of quality. For example, my girlfriend's art versus my art. However, when we go into the making of a thing with the best practices in mind, we can come out with a better product. And in today's video, I'm going to give you 8 specific rules for both making better flashcards and for studying them more effectively. Now, for the purposes of this video, I figured I would need some flashcards of my own to use as examples, so I've gone ahead and issued myself a challenge, and that is to learn and memorize the entire periodic table of elements because, believe it or not, I actually never took chemistry in high school. I had a really busy schedule with other classes at the time and just never got to it. So I've gone ahead and started making some flashcards, which I will be using in the course of this challenge. And we're going to use these to demonstrate the elements of good flashcards. But first, we have to start with a more general tip, which is to simply make your own flashcards. I know a lot of people like to share their flashcards with their friends, and for people who study flashcards on computers or on apps, there are entire online communities where you can upload and download pre-made decks, and I think these have their uses in certain cases, but in most cases, it's going to be much more effective for you to make your own flashcards. One of the most integral and important parts of learning is the process of intaking information and really wrangling with it on your own and creating your own words and your own forms out of that information. That's going to build really strong neural pathways, and those are going to be unique from the neural pathways of somebody else. And if you just take pre-made cards made by somebody else that you didn't have to do any work to create, you're denying yourself that entire part of learning process. So now that you know the importance of making your cards yourself, let's get into the actual nitty-gritty of what makes a card good. And the first tip I've got for you is to add pictures to your cards and to mix them up with words. Now, in cognitive psychology, there's a principle called the picture superiority effect, which describes how people remember images and pictures much better than they do words. And from an evolutionary standpoint, this makes sense. Written language is just a system of arbitrary symbols that people made up, and when we look at things on a grand scale, it really hasn't been around for all that long. Plus, our brains are adapted to be very sensitive to imagery. The locations of food, the animals that'll think you're food, the animals that won't think you're food but will still completely mess you up, etc. By adding pictures to your flashcards, you can make them a lot more memorable. And personally, I like to do this by drawing on my flashcards, but you can also just print out pictures from the internet and glue them on, or if you're using an app or a computerized flashcard program, a lot of them will allow you to easily import pictures. But you can take this one step further by making sure those pictures are next to words. In 1985, there was a study done in Canada that showed that descriptive sentences added next to pictures made those pictures much easier for people to recall. Now, if you take a look at my chemistry flashcards here, you might think they look a little bit weird, but that's actually on purpose because they're demonstrating the third tip I've got for you, which is to use mnemonic devices on your flashcards. Now, a mnemonic device is really anything that helps you create associations between pieces of information in your mind. A classic one is the acronym ROY-G-BIV, which helps you remember the order of the colors in the visible light spectrum, but it can really be anything, and I'm using associative imagery on my flashcards. For example, my flashcard for magnesium has a Magnemite asking for more goulash, which is a completely ridiculous picture, but it helps me remember the association between Mg and magnesium because Magnemite sounds like magnesium, and more goulash is a good way to remember Mg. Now, the more weird and crazy and wacky these pictures are, the more easily you're going to remember them. And remember, you're making your flashcards for yourself, so it doesn't matter what anyone else thinks of them or whether or not those associations would work for someone else. It's just for you. So the next two tips I've got for you guys really go hand in hand. And the first one is to have only one question or fact on each one of your flashcards. Now, doing this is going to help you avoid what are called illusions of competence. Basically, our brains can really easily confuse recognition with recall. When you recognize something, you're basically affirming to yourself that, yes, I've seen this or I've been exposed to it before. But recall is different. Recall is actively retrieving something out of memory without, again, being exposed to it. And our brains can really confuse these things if we're not careful. So here's an example. Say you're taking a history of flight class because obviously airplanes are awesome. And now you're studying for a test where you need to know some information about the first airplane, the Wright Flyer. So you make yourself a flashcard, you put first airplane on the front, but then on the back you put several different facts. And here's where you can run into trouble because later on when you're studying and you see first airplane, you might remember that it flew in 1903, you might remember that it was called the Wright Flyer, and you might even remember that it flew 4 times. But maybe you forgot that it used a sprocket chain drive to drive the propellers. And then you turn it over and you say to yourself, oh yeah, I do remember that. And then you put it aside. So by making 4 individual cards for each of these facts, you're guaranteeing that you're getting each one either right or wrong, and that's going to help you to study the ones you got wrong more efficiently and avoid those illusions of competence. Now, on a related note, we have the 5th tip here, which is to break complex concepts or questions down into simpler questions. And you can run into a lot of situations like this one, where say you're trying to learn the different groupings of elements on the periodic table. And there's lots of them. There's the alkali metals, the transition metals, there's the noble gases. So maybe you go and make a flashcard like this, where all these groupings are different color, and you have to name all of them. Well, once again, this is a bad flashcard because maybe you know some of those groupings, maybe you know all but one, but that one grouping you didn't know, there's going to be an illusion of competence, and you're going to think that you knew it just by looking at the listing on the back. So instead, make flashcards like this that only highlight one of those groupings and make sure that you know it before putting that flashcard aside. So now that you guys know some of the best practices for making your flashcards, it's now time to move over into how to study them. And I've got 3 really important tips in this section of the video for you guys, starting with the first one, which is to say your answers out loud when you're studying your flashcards. And this is kind of just a way to mentally commit to your answer before you actually look at the back of the card, which helps you, again, avoid those illusions of competence. It helps you make sure that you're not recognizing the answer and mistaking that recognition for recall. Make sure that you actually know the answer. Now, the second tip here is to make sure you study your cards from both sides. And this is a way of creating neural pathways in your brain that work in both directions. So that way, if you're asked either side of a question, you'll be able to trace that neural pathway back to the answer. For example, if you only studied the chemical symbol Be and you knew that it stood for beryllium, but then you were later on asked, what's the chemical symbol for beryllium, you might not be able to get back to Be if you didn't study the cards in both directions, so make sure you do. And lastly, guys, my final tip for you here is to realize that flashcards are not a silver bullet. They're just one method of reviewing material, and they are situational. They're just like, say, a bow and arrow, right? You wouldn't use a bow and arrow in every single situation. You wouldn't use it up close, no matter how good of a Hanzo player you think you are. And flashcards are the exact same way. You have to know the right situations to use them in. A lot of information ties into an overall visual hierarchy or an organization, and with flashcards you kind of lose that. For instance, the periodic table is a really, really powerful visual tool. And if you were to say try to memorize all the atomic numbers of the elements with flashcards, you'd really be doing your brain a disservice because learning the periodic table and all the visual representations and relationships is much more effective. Also, make sure that you're learning before you're reviewing, because flashcards often aren't the best tool for teaching you the underlying concepts, which may help you learn facts much more efficiently. So those are my 8 tips for improving the way that you make and study flashcards. And right now you might be thinking to yourself, wait a minute, Tom skipped something. And yes, I did, because there is one additional incredibly effective technique for learning and studying that goes hand in hand with flashcards, and that is spaced repetition. But that's such a complex topic, and I really want to dig deep into it and teach you guys the science behind it and how to use it effectively both on paper and with apps.
All right, so he's not going to talk about spaced repetition, but I will. What I have, it just looks like a plastic container. I bought it at Staples. It holds index cards. Okay, I think it was like $1. It has these little plastic sheets in here. Okay, and it comes with stickers. And you can put the stickers on there, and you can label a tab. So what I did was I labeled mine by daily, 3 times a week, 2 times a month, monthly, and then blank cards. But when I took my astronomy class here, last year, 2 years ago, I made my own cards. Okay, this is a technique that I've done, I've used, I've practiced. I don't know if I still remember all the cards. You know, it's been over a year now. But it helped me to get 100% in that class. Okay, I knew those definitions forwards and backwards. You know, I wouldn't be showing you this technique and giving you the time to do this in class if I didn't see it was beneficial. I'm not saying just because it worked for me, it'll work for you, but it's definitely worth trying because it is a really powerful technique. Once you have really good flashcards made, if you get your card right like 10 times in a row, start spreading it out. You don't have to practice it every day. Use that practice for the ones that you don't know very well. That might sound counterintuitive to some of you, but spend more time on the cards you don't know as well. So what I'm going to do is I'm going to give you the last hour to either catch up on assignments on Canvas, or, so it's going to be like an open lab. If you want to ask questions, you're more than welcome to ask questions. Get started.